Okay, we were on the tail end of number 4, part B for section 2.2, MAC 1105. And we were looking at the graph, talking about how the minimum value occurs at an X value of 3. And we had plugged in that 3 in order to calculate the actual relative minimum value. This is just the X value at which it occurs, as I've been stressing in this problem. So in order to find its Y partner, which is the actual relative min, we plugged it in. This we got right off of the graph. We could see that the low point on the graph was located at an X equal to 3 value. And putting this in the calculator just like this, with parentheses, powers, and so forth, I got a negative 45. Okay, then I wanted to demonstrate how to get the entire answer rather than looking at the graph and seeing that it's a 3 and then plugging it in to get a negative 45. Just backing up that answer and using the calculator as an answer key. So this was the graph. I had demonstrated how to get your calculator to find a max, and in a likewise fashion, you use your calculator to find the min as well. Those functions are found under second calculate, the second to trace button, then just go down to finding a min. Okay, then get the cursor over where the min is, get right on the left side of the min, which is what left bound means. Get slightly to the right, to the left of that minimum value. So even right there, you're slightly to the left, and mark it by pressing enter, telling your calculator, yes, I've given you a left bound. Now it'll say, give me a right bound. So get slightly to the right of that minimum value, which would be approximately there. Mark it by pressing enter. And then it'll say, would you like me to guess at the minimum value? So we press enter again to say yes. And there it is. It has estimated the min. It gives you the exact Y value at an approximate X value of 3. Okay, so just a way to back that up by way of the calculator. Remember, you're using the second calculate feature whenever you want to find maxes or mins. And it'll give you both values, the X value and the Y value. Okay, moving on. So now we're moving on to number 5. Here is problem number 5. And they're asking you to just look at a function that's been given, and just by looking at the powers rather than looking at the graph, because sometimes they're going to give you the problem in the form of a graph, and they're going to ask this same question. Is it even, odd, or neither? So I'm going to have to define what's considered even, odd, or neither in different ways. When you're looking at just the function itself and you want to answer whether it's odd, even, or neither, you can look at the powers. But if you don't have the function and all you have is the graph, then you need another way. You need a definition for odd, even, and neither that includes discussion about symmetry. What axis does the graph wrap around? Does it wrap around the y-axis? Then it has y-axis symmetry. Does it wrap around the x-axis? Then it has x-axis symmetry. Does it have negative counterparts as far as the x and the y coordinate goes in the first and the third quadrant? Then it has origin symmetry. I'll talk about that even further in detail. But when all you're being asked is to look at a function, no graph, is it even, odd, or neither? If all the powers are even, it's even. If all the powers are odd, which is the case here, that's an odd power, that's an odd power, then it's odd. And if it's a mixture of powers, then it's neither. So that one's an odd function. This one is a mixture of evens and odd powers. So this is considered neither even nor odd because it sort of can't make up its mind. In number 7, determine whether this is even, odd, or neither. This is all evens. This is an even function. Okay, then we move on to the type of questions where they present a graph, and then you need to know how to describe even, odd, and neither by looking at a graph. So you have to understand symmetry. What does it mean to be symmetrical? When it is symmetrical around the origin, you're going to see that when it's symmetrical around the origin, now in the outlines that you have, I included some extra bit of information. Right underneath where I gave you this definition right here, I enhanced the definition on the newest outlines as opposed to what I was just showing you. So your outlines look like this. And it says that that the function is odd if when you plug in a negative x value into the function, it ends up changing, that's what this negative out front means, all the signs. If you plugged in a negative here and that same negative here, it would switch this to a negative and this one to a negative. So when the function has that feature, I mean, that's something you can do algebraically to tell whether it's an odd. But with respect to the graph, how do we tell by just looking at a graph if that's all we have? Because sometimes they don't give us the actual function rule in the problem. So when it's an odd function, it wraps around the origin. It's symmetric with respect to the origin. However, being symmetric with respect to the origin can be difficult to visualize. So here is a check that you can do. You can look at the graph, and sometimes it'll be obvious when you get good enough at, looking at graphs. What you're going to have is sets of points that are the same numbers in the first and the third quadrant, or the second and the fourth. So you will have sets of points that are catty-cornered to each other, either first and third quadrant or second and fourth. So like, for instance, let's say in the first quadrant, you have the point on the graph 2, 3. Hop across the origin, 0, 0, hop across 0, 0, and into the third quadrant. And just like you had the point 2, 3 in quadrant 1, you should have -2, -3 in the third quadrant. So the numbers will be the same, but they'll be opposite in sign. And so that is what this definition says. If you can't visually tell that it has origin symmetry, look for any point in the first quadrant. You should have that same point down in the third quadrant. This would be a point in the third quadrant because anything in the third quadrant has a negative x and a negative y. So if you have the point 4, 5, you should also see on the graph -4, -5. If you have the point 1, 2, you should see -1, -2. That's what it means to have points that are across the origin, indicating origin symmetry. Now, those points could also be in quadrants 2 and 4. So if you have a point in quadrant 2 that, let's say, was like this, -2, 3, then you should have that same point in quadrant 4, only it'll be, switch the sign, +2. Switch the y, you should have these two. That would be a point in quadrant 2 and a point in quadrant 4. That would also, they just have to be 2 points that if you're standing on the first one, you have to hop across the origin and into the opposite quadrant in order to get its negative counterpart. And that indicates origin symmetry. So we're going to use this. If they give us, nothing but a graph and they don't give us the function like this so that we can't even see the powers, we're not going to be able to answer whether it's even, odd, or neither in this simplistic way that I've just described to you, where you just look at the powers, all odd, odd, all even. If it's a mixture, neither. If it's all even, even. See, we won't have that to fall back on. So now let's look at... Hey, I also gave you this definition down here in the outlines that you guys have, that when a function is even, this is what's happening graphically. So here we discussed, what it means in the graph if it has origin symmetry. And if the function is even, it should be symmetric with respect to the y-axis. This is when the function is odd. It'll have origin symmetry. When the graph is even, it'll have y-axis symmetry. So when it has y-axis or x-axis symmetry, it's kind of really easy to visualize because you could just crease the paper on the y-axis and you would have matching images on either side. If it had x-axis symmetry, you could crease the paper on the x-axis and find matching images above and below the x-axis. It's the origin symmetry that's kind of hard to visualize, and that's why we have students tell by checking this. All right, so let's look at problem number 8. Okay, so in problem number 8, this is a picture of problem number 8. I transferred those definitions from the previous page onto this page. Notice that if you were to crease the paper right here, you don't have matching images. Because if you did, for this point right here, the point that matches this on the other side would be negative 1, 0, and you don't have that point. So it can't be even. Okay, even functions wrap themselves around the y-axis. In other words, they have mirror images on either side. The mirror image of 1, 0 would be negative 1, 0. So another way to say that is for any point that is one space away from the y-axis, you should have one that is one space away and having the same coordinate. You don't have that. Odd functions. Odd functions I just described on the previous page that you should have matching points. Like that. So you should have matching points. And I could give you like a little example of this, how you could check whether it's in your calculator, just so you understand this definition easier. Here's an example of an odd function. Okay, x raised to the third power. Nothing but odd powers. So it's going to have counterpart points in the first and the third quadrant. See, you graph it. Let me change this to a standard window. Okay, so it's a little bit more spread out. So what that definition says, I'll slide this calculator down, is that when it's an odd function, in order for you to tell that it has origin symmetry, you should be able, for any point that you find in the first quadrant, you should be able to find that same point just with opposite signs. That would be the point in the third quadrant. Okay, if you don't have that going on, matching points in the first and third quadrant, then it's not an odd function. So we can check that on your graphing calculator by going to the table of values that your calculator creates before it graphs this thing. Okay, so you would just go second table, second graph, and you'll see the table. So let's go find a value that's in the first quadrant. Like for instance, anything that's positive, positive. See that right there, 2, 8? And it doesn't have to be this point. You can check any point. Look, for 2, 8, do you see that right up here? You have the same point in quad 3, negative 2, negative 8. You want, the only thing you can't check is the origin. For 1, 1, this point 1, 1, do you see that you have those same numbers but with negatives in front of either one, negative 1, negative 1? That means that this thing has origin symmetry, and therefore it is an odd function. Okay, but is that happening? I'm just demonstrating to you what an odd function is. Is that happening in this particular function that I'm showing you? Notice that for 3, 3, you don't have negative 3 down here. So because there is a point in quad 1 that you can't find the counterpart for, if this was an odd function, you'd be able to find negative 3 down here, and you can see that it doesn't go through that. So it's no to being an odd function. So if it's not even and it's not odd, it is neither. Okay, that's the answer to number 8. Number 9, so that's telling whether it's odd, even, or neither just by way of the graph without actually having a function in front of you. Okay, moving to number 9. Now I'm going to probably have to do this problem on the next video. So I guess I'll just stop this here and continue this problem on the next video.